Assalamu alaikum. Welcome to the new lecture. In this lecture, we'll be discussing about the capacitance of a single core cable, capacitance of a three core cable, and the uh, grading of cables. Let us start with the capacitance of a single core cable. As we know that a single core cable can be considered to be an electrostatic capacitor because of presence of two electrodes. One is at the earth potential, that is the sheath, that is this, and another conductor which is at a certain potential, and they are at a distance at a certain distance apart from each other. In this case they are at a distance of capital R minus R, and instead of um, having the air as the medium, there is a particular dielectric which uh, is in between these two electrodes. So we can consider this to be a capacitor, like we considered this wire line as a capacitor, where one electrode was considered to be the conductor and another was considered to be the earth. So let lambda be the charge per unit length. By definition, capacitance is the ratio of the charge on one of the electrodes to the potential difference between the electrodes. So we know that this derivation or this formula we have derived in case of corona as well. So here voltage we can calculate, it will be equal to lambda. In the topic corona, we have considered there this to be Q, where Q was also uh, defined as charge per unit length. So here we have defined it as lambda, which is have the same units, that's charge per unit length. So it comes out to be lambda divided by 2 pi epsilon ln of R, capital R by R, where capital R is the radius of the sheath from the center of the conductor and small r is the radius of the conductor. So when you take the ratio of this lambda by V, you get the capacitance will be equal to 2 pi epsilon ln of capital R by R farad per meter. You will see that if you remember the capacitance of the overhead line, that was also of the similar form, that is 2 pi epsilon ln of D by R, where D was the distance between the two conductors. But here the distance between the conductor and the sheath is very small, so this term will be small, the capacitance will be very much larger. Also, in case of overhead line, this E was not directly epsilon, it was E in epsilon naught, because the medium was the air, and we know that epsilon naught for air is always taken to be equal to 1. In that case also you will see that capacitance of underground cable is more than that of the overhead conductors. So that's what is written over here. The capacitance of a cable is much more important than that of the overhead line because of the nearness of the conductors to one another and to the earth sheath. Also, the permittivity of the dielectric material is higher than that of the air. So it is more important because its value is more, so we cannot neglect it in the practical purposes. Now, similarly, we can calculate the capacitance of a three-core cable. So if we assume that the dielectric is a uniform between the core and the sheath, core means conductor, it is possible to calculate the capacitance of a three-core cable, but normally it is not so. Therefore, it is desirable to find the capacitance by measurements, and we always try to do this. We calculate the capacitance by doing some measurements. In a three-core cable, sheath is at earth potential, that is always the case, and the three conductors are at the supply potential. We are charging the conductors rather than the sheath. Sheath will be always connected to the earth, that's why it will be at earth potential. There are 6 capacitances formed between these systems, you can see. For example, this is 3 conductors, conductor 1, conductor 2, conductor 3, and this is the sheath. Now the capacitance will be 6 capacitances, that is conductor and sheath, conductor and sheath, conductor and sheath, and let these capacitances be denoted by C1. And there are other 3 capacitors which are formed between the conductors itself. That's conductor to conductor, that is C2, conductor to conductor, that is this C2, and conductor to conductor, that is this C2. 3 capacitors are between the sheath and the conductor, that is C1, and other 3 capacitors between the conductors, that is C2. You can see between the conductors. So we call this capacitance between conductor and sheath to be C1, and capacitance between the conductors to be C2. So now it is very difficult to solve this circuit because it's a delta. Converting this to star, when we convert delta to star of equivalent impedance, because it has the same capacitance, its impedance or reactance will also be same. So when a delta is converted to equivalent star of same impedance or resistance, you will see that in equivalent star, the impedance of the star will be the impedance of the delta divided by 3. But since capacitance comes, the impedance and the capacitance of a capacitance of any capacitor are inversely related to each other, because the impedance or reactance of this capacitance will be equal to 1 divided by omega C2. So when that is divided by 3, so its impedance will be, or the impedance of this star will be equal to 1 divided by 3 omega C2. That means its equivalent capacitance will be increased by 3, because you will see that in denominator will be 1 divided by 3 omega C2. So equivalent capacitance will be 3 C2. So that's why here in star the capacitance will be 3 C2. So the equivalent circuit for this case will be now like this. So this ground means this is the earth potential, that is the S means sheath. Let's say this is point A, this is point B, this is point C. You can see now this will be like this. Equivalent star is 3C2, 3C2, 3C2. This is C1, C1 and C1. Now what is important? This is the per phase capacitance. This one, let us say between A and N, or A and we need to analyze this circuit. Now this is conductor, point A, which is conductor, and this is earth potential. This is also earth potential, this N. So you can see these two capacitances at this point share the same node, and at this point you can see this is actually the same node at a different point. So they are not actually in series, they are in parallel, because here one uh, we can say one point or one connection of this, or one electrode of this capacitance is connected to point A, and another electrode of these two are connected through S and N, because S and N are at the same potential, or we can say they are connected to each other. So we can say these two are in parallel. C1 and C32 are in parallel. This is the conductor and this is this point N. So the per phase capacitance that is in one phase, that's phase A, is C1 plus 3C2. C1, this is the equivalent of the whole this three core cable capacitance. The star point is the sheath potential and the other terminal corresponds to the conductor of the cable. The whole system of the capacitance can be reduced to the following system, that is this. So in this case, so the C naught, which is the per phase capacitance of the three core cable, will be equal to C1 plus 3C2. From here, there are two unknowns, that is C1 and C2. For this cable, these unknowns are calculated by doing different measurements. So there are different measurements. We can use two measurements for calculating this. The first one will be we bunch or we connect all the conductors to each other like this, and in this case we are actually eliminating these two C1 C2 capacitances. When these two are connected to each other, you can see one point or one connection of these capacitors, that is C1, are now connected to each other. Another point is already connected to each other through the sheath. That means this C1 will be parallel to this C1 and this will be parallel to this C1. And when you look at these points, when you measure these capacitance from this, you will get Cx, and that Cx will be actually the parallel combination of C1 and C1. That means Cx will be equal to 3 times C1. So from here, bunch the three cores, that is conductors, and measure the capacitance between the bunched conductor, that is one is this bunched conductor, and the sheath. So we have measured this capacitance between this point is actually similar. You can measure this from this point to this point also, because this point is same as this point and this point is same as this point, so it will give the same measurement. Similarly, you can measure this conductor and sheath. This point is same as this point, and again this point is same as this point. You can measure it at any conductor and between the sheath, you will get the same answer. Now second measurement is done between when connect the two cores to the sheath. We have connected these two cores to the sheath. That means we are actually bypassing these two. C1 and C1 will be neglected. Similarly, C2 cannot come into measurement, because you can see why. and measure the capacitance between the remaining conductor, that is this conductor and the sheath. So we have to connect these two conductors to the sheath. We have to bunch these conductors to the sheath and then measure the capacitance between the third conductor, which is not connected to the sheath, and to the sheath. So this is why Cy is calculated. Now this point is connected to this sheath, this point is connected to this sheath. When you calculate capacitance between this point and sheath, that means you are calculating capacitance between this point and any point on this sheet. So you can see that there are three capacitors, C1, C2 and C2. One connection of all the capacitance is connected to this conductor. Another connection of all the three capacitances is again connected to the same point through this point. You can see here it's one point is connected to this sheath through because it is bunched through this. Another point of this connection is connected to sheath again, and this point, the another terminal of C1 is connected to the sheath. That means again these three will be parallel to each other. So they will look like this: C1, C2 and C2. That means C1 will Cy will be equal to C1 plus 2i C2. So this is actually the intermediate, we can say intermediate equivalent circuit of this. This is C1 and C2 and C2 will be parallel to each other. You can see from here C2 and C2 will be parallel to each other, and the intern will be parallel to C1 as well, like this. So in this case Cy will be equal to C1 plus 2i C2. With these two measurements we can calculate the value of, because we have two equations and two unknowns, we can calculate the value of C1 and C2. So from first, since the Cx is equal to 3C1 and we have calculated the value of Cx, then C1 will be equal to Cx by 3. That's what I have written over here. Similarly, since this Cy is equal to C1 plus 2C2, so C2 will be equal to Cy minus C1 divided by 2. That's what, which is more, that is C2 is equal to 1 by 2 Cy minus C1. Cy is that is as it is, and C1 is equal to Cx by 3. This is C2. So capacitance per phase, as we know, is equal to C1 plus 3C2. C1 is Cx by 3. 3 is as it is, and C2 is equal to 1 by 2 Cy minus 1 by 2 Cy minus Cx by 3. That's 1 by 2 over here. That comes out to be in this divide Cy minus Cx by 3. So when we multiply it, it comes out to Cx by 3 plus 3 by 2 Cy minus Cx by 2. That means this 3 by 2 Cy as it is. When you simplify these two terms, that is Cx by 3 minus Cx by 2, it comes out to be minus Cx by 6. So from this formula you can directly calculate the per phase capacitance of a 3-core cable. Now let us try to find out one numerical from here. A 3-phase 3-core metal sheath cable gives the following results on the test for capacitance. Capacitance between two conductors bunched with the sheath and the third conductor is 0.4 microfarad per kilometer, that is this is equal to Cy. Capacitance between bunched conductor and the sheath is equal to 0.625 microfarad per kilometer. This is Cx. Determine the capacitance between the two conductors, between any two bunched conductors and a third conductor if the sheath is insulated. Also calculate the charging current per phase per kilometer when it is connected to a 10 kilovolt 50 Hz supply. We'll first use this because this will directly give us one unknown. So Cx is equal to 3C1 is equal to 0.625. So C1 will be equal to 0.625. So C1 will be equal to this 0.208 microfarad per kilometer, because this is also given in microfarad per kilometer, 0.208. Yes. So Cy is equal to C1 plus 2i C2. Calculating the Cy will come out to be 0.096 microfarad per kilometer. So this is the calculation of C1 and C2. Then C0, putting the value of the direct value of Cy and Cx. So the 3 by 2 Cy minus Cx by 6 is equal to 3 by 2 into 0.4 minus 0.625 divided by 6, that is equal to 0.496 microfarad per kilometer. This is the value of the per phase capacitance. The capacitance between any two conductors will be divide by 2. When you divide by 2, it comes out capacitance between the two conductors, it will be equal to 0.248. You know it before when we calculate the capacitance between the capacitance calculation between the conductors, we first calculate the capacitance between conductors, and then when new conductor to neutral, we simply multiply that by 2. Here we know the capacitance between the conductor and neutral. Here we have to calculate between the conductor, we simply have to divide by 2. Now the second one, so C1 and C2 calculate the equivalent circuit for measuring the capacitance between two bunched conductors and the third conductor. That means we have to bunch the conductors to itself, not to the sheath. You can see in because sheath is insulated between any two conductors and the third conductor. We have to calculate between any two bunched conductors. We first have to bunch two conductors. Let us say we bunch these two conductors. When these two conductors are bunched, you can see this C2 and C2 will be parallel because their one terminal is connected to this point and the terminal will be connected to each other through this bunching. So that means this C2 and C2 will be parallel, that is this, and this C1 and C1 will be parallel because this is connected to this one terminal and the connection will be this is connected to this. So this will be let us bunch this point and this point. When we bunch this point and this point, this C1 is that is C1, that is this C2 and C2 will be parallel, that is this, and this C1 and this C1 will be parallel, that is this, and this connection is connected to each other because of the sheath, because sheath connected them like this. So then after that we have to calculate the capacitance between any two bunched conductors. That means between this point and this point, any of these two, because they are at the same potential, and the third conductor, and the third conductor is this. That means we have to calculate the capacitance C between these 2 points. So you can see this will be C2 twice C2, this will be twice C1, and then this C1 twice C1 and this C1 will be in series. The series combination will be equal to 2 by 3 C1, and then their combination and their combination will be in parallel. So this will be twice C1 plus 2 by 3 C1. So substituting the value of C1 and C2, the capacitance, that is C, will be equal to 0.33 microfarad per kilometer. Now the third is the charging current per phase per kilometer will be, simply you have to put the value of capacitance, that is V omega C. So you have to use the per phase value of the capacitor is voltage, that's V by root 3 into omega C naught, that is 10 divided by root 3 into 314, that is this 100 pi C naught you have calculated, it comes out to be 0.899 amperes. So I hope you have understood this. Now one more miracle, at 33 kV 50 Hz 3-phase underground cable 4 km long uses a 3 single core cable. Each of conductor has a diameter of 2.5 cm and a radial thickness of insulation is 0.5 cm. Determine the capacitance of the cable per phase, charging current, total charging kVAR. The relative permittivity of the insulation is 3. So capacitance of the cable per phase, here the formula has been used in terms of log of 10 and it has used already 2 pi. You can directly use 2 pi epsilon naught into epsilon r into L divided by ln of r by r, where r is equal to this conductor diameter and the radial thickness of the insulation is this. So radial thickness is this, so d, that means r. Here it has used d, but you can use r. R is equal to 3.5 centimeter. That means it will be equal to C is equal to 2 pi epsilon naught epsilon r into L is the length of the conductor divided by ln of r by r. R is equal to this 3.5, r is equal to 2.5, and giving the value you will get the same value. That's 1984 into 10 raised to the power minus 9 farad, or 1.984 in microfarad. So charging current will be equal to V omega C, that is V phase omega into C, that's 100 pi into C into, this is C into the phase voltage, that is this. It comes out to be 11.87 amperes. Total kVAR will be equal to 3 times V phase into IC, 3 V phase into IC, it comes out to be this value, 678.5 into 10 to the power 3 kVAR, or if you convert into MVAR, it will be equal to 678.5 MVAR. So this is how to calculate the single phase capacitance and charging current along with the kVAR. Now the grading of free cables, it is actually the similar topic that we have uh, studied regarding the insulators, there also we use the grading of insulators, and the purpose is the same, just to make the uniform voltage distribution across the dielectric of the cable. There we try to uniform we try to make the uniform voltage distribution across the insulators. Here we try to make the again voltage uniform voltage distribution across all along the dielectric. By grading of cables, we mean that the distribution of dielectric material should be such that the difference between the maximum gradient and the minimum gradient is reduced. Thereby, the cable of the same size could be operated at higher voltage, or the same operating voltage can be relatively same operating voltage of the cable of relatively smaller size could be used. So this is the prime motive of the grading of the cables. There are usually two methods of grading of cables. One is the capacitance grading, where more than one dielectric material is used. Another is the intersheath grading, where the same dielectric material is used, but potentials at certain radii are held at certain values by interposing thin metal sheets, and they are forcibly kept at a particular voltage distribution. We'll see that one by one. Let us start with the capacitance grading. Let again, lambda is the charge per unit length. If we have one single dielectric material, the gradient at any radius x will be, as we know that this will be equal to gradient, that will be equal to lambda divided by 2 pi epsilon x. This you can calculate, which is E. You can calculate by using this Gauss law. So in this case, where E is the permittivity of the material, if we could use an infinite number of materials with a varying permittivity, whose permittivity is given by epsilon is equal to k by x. This is a hypothetical theory which may not be in practice used, but we can use this and see what is the effect. So the permittivity of all the materials which are very close to each other, and the number of materials will be infinite, so its permittivity will be equal to k by x. That means the permittivity which is close to this will be having the higher value, and as we go from this the radius of the conductor or the surface of the conductor towards the sheath, their permittivity will decrease as per this relation. So the gradient at any point x now becomes, now you can see the gradient at any point from x becomes, that is this, you can see when you replace this E, that is epsilon divided by, replace it by k by x, so it will be 2 pi into k by x into x and x will cancel out to be constant. So the gradient, we can see gradient of this dielectric with infinite number of materials will be like this. It will be constant from this r is equal to small r to r is equal to capital R, which is actually a non-ideal case. For a particular operating voltage, the overall size of the cable is minimum when we use infinite number of these sheets. This looks quite alright, but practically it is impossible to have an infinite number of dielectric materials with varying permittivity as given above. It's very difficult and it becomes particularly or practically impossible and uneconomical. Normally 2 or 3 materials are used. What we do usually, we are using only 2 or 3 materials. Let there be 3 materials with permittivities epsilon 1, epsilon 2 and epsilon 3 placed at a radii r. That is, one is placed at a radii r, the second one is placed at r1, and the third one is placed at r2 respectively. That is, one is placed at here, another is placed at here, another is placed at here. Let all the materials are subjected to the same maximum stress, that is Gmax. So we assume that all have the same maximum stress. You can see from here, we'll see this. This is the maximum stress of this value, this is the maximum stress of this value, this is the maximum stress of this, and after that it will decrease definitely. So Gmax will be equal to lambda divided by 2 pi epsilon 1 r. For this case it will be lambda divided by 2 pi epsilon 2 r1, and for this case lambda divided by 2 pi epsilon 3 r2. This is for this material. So when this happens, that means epsilon 1 r, because these 3 are constant, lambda 2 and pi, so that means epsilon 1 r should be equal to epsilon 2 r1 should be equal to epsilon 3 r2. So with this, since r is less than r1, which is less than r2 from this geometrical configuration, and it will always be like this, that means E1 has to be greater than E2 has to be greater than E3. So the dielectric material with highest permittivity should be placed nearest to the conductor, and the other layers will be in descending order of their permittivities. So this is very important. So when we have to use different dielectrics for a cable, so in that case, the dielectric material having the highest permittivity has to be placed near to the conductor, and with the decreasing order of the permittivity, we have to place other dielectric materials. So the distribution of voltage using capacitive grading for same truss is shown in this figure. So you can see have the same maximum dielectric strength at the surfaces, and by using this, we have calculated or we have derived the formula. Therefore, the total operating voltage of the cable, if Gmax is the working stress, will be equal to the operating voltage for this case will be equal to Gmax or ln of R1 by R. Actually, we have derived this. Similarly, for this case from R1 to R2, it will be equal to Gmax R1 ln of R2 by R1, and for this much, it will be equal to Gmax R2 ln of R by R2. That means for this hashed area. So since Gmax is same, it comes out to be this. We have taken Gmax outside. So let us try to do one example on this, which is slightly different from this. We have not assumed in this numerical Gmax to be same. A single core lead covered cable is to be designed for 66 kV to earth. So it is to be designed for this voltage. Its conductor radius is 0.5 cm and it is 3 insulating material ABC has relative permittivities 4, 2.5 and 4. Since from this derivation we have devised that their permittivities should be different. Highest permittivities to be placed near the conductor, and the other permittivities are placed as per their decreasing order of the permittivity. But here the two materials have the same permittivity. Let us see what we do with these permittivities. With the maximum permissible stress, but stress is given which is not same. You can see over here 50, 30 and 40 kilovolt per centimeter respectively. So determine the minimum internal diameter of the lead sheet. We have to calculate this R. Discuss the arrangement of the insulating material. We have to also find out the which material to be placed where with respect to the conductor. In order to have a minimal internal diameter of the lead sheet and consistency in electricity, it is desired that the material to be placed near the surface of the conductor should be one with maximum of the product of electric stress and permittivity. Here it is not only the permittivity, here is the product of electrical stress and permittivity, whose product should be, when the electric stress and the permittivity product is more, we have to place it near the conductor. So in the case material A, the product is 4 into 50 because material A has a permittivity of 4 and this is 50. It comes out to be 4 into 50 is 200 as the maximum and will be placed near the surface. This will be the maximum because you can see the second one is 2.5 into 30. It comes out to be 105. No, it will be 75. Yes. So the third one is 4 into 20. It is 4 into 40. It will be 160. And the material C has the product of 4 and 41, so it will be placed next, and then the material B. Then the material B. This will be material A, this will be material C, this will be material B, having 4, 4, and 2.5. Here R is equal to 0.5 centimeter. Let Q be the charge per unit length of the cable. Here we are using this relation. Gmax is equal to Q divided by 2 pi epsilon R. But Q is again the it is, or we can see this lambda divided by 2 pi epsilon R. So this is G1 for material 1. So using this relation, G2 is equal to Q divided by 2 pi epsilon R1. I'm here telling this epsilon not in epsilon to be epsilon itself because epsilon will be equal to epsilon naught into epsilon R. G3 is equal to Q divided by epsilon naught epsilon 3 into R. So multiplying these, this Q will be equal to multiplication of this and this. This Q will be multiplying this and this, and this Q will be equal to multiplying this and this. Q is same in three cases. In all the three cases, we can equate these three equations like this. So 2 pi epsilon naught, 2 pi epsilon naught, and 2 pi epsilon will cancel out. So here this E1 R G1 max will be equal to E2 R1 G2 max will be equal to E3 R2 G3 max. From these two relations, this R1 by R, that's R1 by R is equal to E1 G1 max divided by E2 G2 max. These are all given. So R1 will be equal to, this is 200 This is 160 multiplied by 0.5. This R is given, which comes out to be 0.265 centimeters. This R1 is. Similarly, from these two equations, this R2 by R1 will be equal to E2 into G2, E3 into G3 multiplied by this R1. So E2 into G2 will be 160, E3 into G3 will be 75, it comes out 1.33 centimeters. So V, which is given to be equal to 66, and also you need to be very careful. Here it is given to be to earth. If it is given to be line voltage, you have to divide then here by 66 by root 3. So it comes out to be R G1 max ln of R1 by R plus R1 G2 max ln of R2 by R plus R2 G3 max ln of R by R2. Please try to, this is actually the same equation, the equation that we have just used. There is only one difference, that this G max is not same. It is G1 max, G2 max and G3 max. The rest is same. You can see over here G1 max, G2 max, G3 max. So all the quantities are known in this equation, only R has to be calculated by putting this value of this, and R comes out to be equal to, sorry, this R comes out to be equal to 2.8325, and calculating the D, that is the diameter of this sheet, it is equal to 7.53 centimeters. I think today it is enough. Thank you very much.